So a monoprotic has only one proton per molecule. Those are some examples. You can see there's only one hydrogen on each of the molecules. Are those strong or weak acids? Strong. What are the 6 strong acids?
What are the 6 strong acids?
Yeah.
HCl, HNO3, HClO4, H2SO4,
Yep. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. We need to know those 6. And then there's only one ionization step. Whoops.
So
Jackie says no.
can it be like an acid and base, like on our worksheet when we have to do that?
In a reaction, it will only act as an acid or base. In a different reaction, it might act as a base instead of an acid,
So,
but
water could act either as a base or an acid depending on the reaction.
yes, depending on the reaction. It won't act as both in the same reaction. So polyprotic, what do you think polyprotic would be?
2.
Poly means more than one. There's a special term for, what would special term for 2 be? Di. And special term for 3 be tri, yeah. So poly means more than one. More than one proton per molecule. So here's some examples. See how there's 2 hydrogens here, there's 3 hydrogens here. So you're going to have multiple ionization steps. So first, if you look at sulfuric acid reacts with water to give us, it loses 1 proton at a time. So you get HSO4 minus plus H3O plus. And then the HSO4 minus reacts with the water, and you get sulfate and hydronium. Now look at the difference between these reactions. One has just a single-sided arrow. One's a double-sided arrow. Sulfuric acid is one of our strong acids, so it completely deionizes. So it's going to completely ionize, and it's all going to turn into HSO4 minus. HSO4 minus, is that one of the strong acids? No. H2SO4 is, HSO4 minus is not. So that's why we have a double-sided arrow here, because some of it will ionize, some of it will not. So it goes back and forth between being this form versus the sulfate form. So that's one way we can use arrows and show in the reaction whether it's a strong or weak acid also. So then some special polyprotic acids. A diprotic acid is a type of polyprotic acid that donates 2 protons. So sulfuric acid is a diprotic acid. Triprotic can donate 3, like phosphoric acid. Okay, Lewis acids and bases. This is just going to be another way of defining what an acid and base is, like the Arrhenius theory and the Bronsted-Lowry. We have the Lewis acid and bases, and it's all based on electrons. So an acid accepts a pair of electrons. So it's looking at the transfer of electrons, and bases donate a pair of electrons. Much more general definition, because a lot of different compounds and molecules can be in this definition. Now, and also, if you look at this, in the Bronsted-Lowry definition, acids donate protons, right? Here, in the Lewis definition, acids accept electrons. So they're opposite. We will usually use the Bronsted-Lowry definition. The Lewis acid definition is not very, it's more general. We don't use it as much. So in this one, this reaction, which one's acting as the Lewis acid? This BF3, boron trifluoride, because it's accepting these electrons. Nitrogen in the ammonia is acting as the base. So for identifying the Lewis acid and Lewis base here, we have to kind of think of the Lewis structures. Aluminum has how many valence electrons? 3, and if it has 3 chlorine attached to it, that means it looks like, if my pen comes up, here we go. So does aluminum have any other valence electrons in order to bond with anything else? No. So can it donate any electrons? It's probably going to accept, correct? So it's going to act as, here's our acid, because it's going to have to accept, this is going to be our base. And there's 2 lone pairs of electrons around this oxygen, that's where those electrons are going to come from. Extra H's. No.
There's 10 on that side, and then there's only.
There's 10 here. Okay, what about this one? Let's check Cn minus. There's 4 here. So we have a triple bond here. Okay, and oops. So is it going to be able to donate electrons? Yes, I'd say that one can donate. So this is going to probably be our base since it's donating electrons, and this would be our acid. It's going to accept the, because mercury Hg. Oh, yeah. It's not going to be able to donate any. Okay. That's just a couple examples. We really aren't going to be using this theory as much as the Bronsted-Lowry theory. Okay, and then conjugate acid-base pairs. In any acid-base reaction, there's always 2 conjugate acid-base pairs. It's all related on the gain and loss of protons. So we're going back to the Bronsted-Lowry definition. You're looking at, as it's acting as an acid, so this A is just a generic anion, B is just our base. So after this acid has lost its proton, what does it look like? It's going to be just A minus. So we have, this is our acid, this would be considered our conjugate base. Since this is our base, this is our conjugate acid. That's how they're paired. So it's all based on what they look like after they've gained or lost a proton. So the species that remains after the Bronsted-Lowry acid has given up the proton is the conjugate base of that acid. And the opposite is true of the base. The species that's formed when the Bronsted-Lowry base gains the proton is the conjugate acid. So after the acid has donated its proton, it is now the conjugate base. After the base gains a proton, accepts the proton, that form would then be the conjugate acid. And I'm pretty sure we have an example of that coming up here. Think of let's just look at HCl plus water. What would we get here? We're going to get chlorine or chloride plus hydronium. So which molecule is acting as the acid? HCl. It's donating the proton. Which one's the base? Water. So which one's our conjugate base? you look at your acid, and after it donates its proton, what form does it take? Cl. So this is our conjugate base. And then this would be after the base has accepted its proton, it is now hydronium, so this is our conjugate acid. So that's how they're paired. So we have 2 pairs in each reaction. Okay, in this reaction, hydrofluoric acid.
At this time, if we could have the varsity choir report to music, I didn't maybe probably report to the auditorium, if you can. If you're in class and you're taking the test or something, if not, varsity choir, just report to the auditorium. Thank you.
We're going to do something?
We're going to finish notes.
No, but we're going to do something?
Do something. So the hydrofluoric acid donates the hydrogen. So its acid form is HF. After it donates its proton, it's now fluoride, and that would be the conjugate base. Whereas water is acting as the base again, so it's the conjugate acid. Okay. Now they've just split the reaction into 2 parts, so it'd be HF plus H2O yields fluoride plus hydronium. They've just split that reaction. Okay. Can I switch it? So this is just showing that same reaction again, just putting it all together. Loss and gain of protons, that's what it's all related by. Yeah, so let's go to the problems. Can I switch it? Or
No. Whoa.
no.
Switch it.
Ready? Just showing you another example. Okay, write the conjugate bases of the following. So if they're one in the conjugate base, that means these are acids. And what do acids do? They give up a proton. So what would be our conjugate base of this acid? After it gives up a proton, what is it going to be? All you got to do is take off the proton. So we would just have Br. And what charge would it have? Negative, because hydrogens are +1. So if you're taking away a +1, you're now 1 more negative. How about H2S? What would be our form? Take off 1 proton. And you have a -1 again. H2CO3. And the -1 again, yes. Okay, so that part's easy to write it out once you figure out what you need to do. So if it asks for the conjugate base, that means that that molecule was the acid, and acids donate. Now, the next one says write the conjugate acid. So what are those compounds? Those compounds must be a base, because conjugate acids are paired with bases, and what do bases do? Accept a proton. So we add a proton to it, so what would we have? HNO2. And it was -1, and we're adding a positive, so what charge does it have now?
Plus.
It's neutral. Because it was -1, we're adding a +1, so it's neutral, yes. So it's neutral. NH3, we're adding a proton, so what would it be?
NH4.
NH4, does it have a charge?
No.
Yes.
Yes, it does, because it's neutral, and we're adding a +1 to it. So this time it's a plus charge. Is there a 3? I can't see the number 3.
Will this be the last chapter?
OH negative. So OH negative, what do we add to it? So we'd have add a proton and we get H2O.
Yeah.
Yes.
Hey,
What?
is next week our last full week of school?
No.
Oh, that's garbage. Yeah, it is.
Is
This
it?
week's conference, next week's is districts, then that next week is state track. State track's on like the 20th. No, wait, no. That third week we get out like Thursday.
Yeah.
Yeah, there we go. Okay.
Next week we have a full week.
Yeah, next week we do, but not the next week. Yeah, it's our last full
Uh,
Awesome.
Okay, we need to determine whether they have an acid-base conjugate pair. Acid-base conjugate pairs are related by just the gain or loss of protons. So we're looking to see if it's one proton different from each other. Are these one proton different from each other?
Yes, ma'am.
Yes, so let's circle them. That's a yes.
How do you know?
Do this.
Because it just has one proton here and 0 protons here, but everything else is the same. So this one has just lost the proton from that form.
All right.
How about number 2?
Yes.
No, because it lost 2. We're just looking at one step, okay? If it wanted multiple ionization steps, it would tell you specifically, but we're gonna say no on that one. How about this one?
No.
No, we've changed oxygens too, and we don't want to. When we look at conjugate acid-base pairs, it's only hydrogens that are changed. How about number 4? Yes. We've just changed one hydrogen. And number 5? Yes. We're only one hydrogen different from each other.
Can we be done?
I'm looking to see.
Be done.
This is still about the conjugate acid stuff. So if we have a strong acid, when you look at its conjugate base pair, it's going to be a very weak conjugate base. So the stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. If you have a really weak acid, you're going to have a very strong conjugate base. Weak bases are going to have very strong conjugate acids. And there's a table in your book, table 6, that lists the strengths of the acids versus their conjugate bases. You can look at that. I think. One more slide. So this last slide. Yep. This is the last one. Amphoteric compounds are compounds that are able to act as either acids or bases. Not in the same reaction. But if it reacts with one compound, it might act as a base. If it reacts with a different compound, it might act as an acid. So you might have noticed on your worksheet that water acted as both an acid and a base, depending on what it was reacting with. And so it is an amphoteric compound. That is probably the most common example of the amphoteric compound, because it can act as an acid or a base. Okay.